can hear me well. So welcome to our Inorganic Chemistry course. We will be starting today our discussion on solid-state chemistry, as I mentioned last Friday. So this marks the beginning of the second part of our course, in which we will be covering several aspects related to solid-state chemistry. And this is a very important topic in inorganic chemistry, as solid-state materials have played a central role towards several important applications, from batteries to generation of new catalysts and devices to tackle important global issues in the areas of clean environment, fighting pollution through plastic recycling or photocatalysis, for example, and the generation of green energy, such as catalytic materials for this water splitting processes, for example, or the water splitting reaction to generate hydrogen to be used as the fuel of the future. So we will have a total of 3 lectures covering several aspects of solid-state chemistry. So our agenda for these lectures will cover the description and understanding on the structure of solid materials. Then we will talk about metal and alloys, which play a very important role among all solid materials in inorganic chemistry. Then we will discuss also ionic solids and covalent framework solids. Here, covalent framework solids also have emerged as an important class of materials, such as metal organic frameworks, for example. Regarding these materials, we will discuss several qualitative and quantitative aspects of ionic bonding. So we will describe how we can study the energetics of ionic bonding. Then we will also cover defects in non-stoichiometry, which is very important because many defects in solids and the occurrence of non-stoichiometry usually leads to several interesting properties in solid materials that can be harvested for different applications, such as conductivity and also catalytic applications. And then we will finish by discussing the electronic structure of solids, in which we will discuss bonding, and which will allow us to understand and to describe the properties of metal, semiconductor, and insulator materials. Okay, so as I have mentioned in this course, I believe that solid state or solid materials, like the study of the solid state, is central to many important inorganic materials that play a central role in several important applications of chemistry nowadays. And these examples of important inorganic materials comprises metal alloys, simple metal salts, graphene, several oxides and sulfides and selenides that are used as inorganic pigments, several classes of nanomaterials, zeolites, and also high temperature superconductors. And in this course, the idea is to cover the structures that are adopted by atoms and ions in simple solids. So we will start by describing these structures for simple solids and simple solid structures and geometries, in which we will begin with the simplest model. And then in this simplest model, we can consider each individual atom to be represented by hard spheres. Here, hard spheres means that spheres that don't interact directionally with each other. So then we just consider how these hard spheres pack. into 3 dimensions to give the structure of the solid of interest. And then we will use these simple structures as the building blocks to construct or to build or to describe more complex inorganic materials. All right, so we will also describe the energy considerations that can be used to rationalize trends in structure and reactivity of these solid materials. Then we will also cover how electronic structure in solids can be described, and then we will see how this is different from, for example, from atoms and molecules. In this case, the electronic structure of materials can be described in terms of the band theory, which then describes the energy levels that electrons may take place in various solids. And this band theory, or the electronic structure of the materials, enables us to classify inorganic solids as conductors, semiconductors, and insulators. All right, so let's start by discussing the structure of simple solids. It's important to keep in mind that the majority of the elements and inorganic compounds, they exist as solids, and these solids display an ordered array of atoms, ions, or molecules. So solids represent an important class of inorganic compounds and elements, and in these solids, usually the building blocks that make up this solid, such as atoms, ions, or molecules, they are organized in an ordered array. And in the case of metals, for example, the structure of most metals can be described in terms of a regular or ordered arrangement of metal atoms, in which we can consider these metal atoms as hard spheres, so we can use a space-filling arrangement of the metal atoms, or the organization of these atoms in 3 dimensions, and how they fill up the space, or how can they be organized into these 3 dimensions to fill the space to make up the solid material. And then we will see these kind of structures very soon. So these metals centers in this structure comprising the metals, they interact with each other through metallic bonding, in which the electrons are delocalized over bands of energy and therefore are delocalized throughout the entire extension of the solid material. And so the metallic bonding occur here for metals. And as we saw in the first lectures in this course, the metallic character depends on the our characteristic, like a high metallic character, are characteristic of elements with low ionization energies. Therefore, this metallic bonding, or the formation of metallic bonding, is characteristic of elements displaying low ionization energies, such as those on the left of the periodic table through the D block and part of the B block close to the D block. So are the areas also where size increases. So in terms here, discussing briefly what the band theory, or what is the metallic bonding in terms of the band theory is, we can understand this by taking a look at this diagram, which shows orbitals as a function of the energy here in the y-axis. So what happens when we have, like, let's consider the valence orbital here for a metal. Let's here consider lithium. So when we have one lithium atom, we have the electron configuration, and here the valence or the outermost orbital is a 2s orbital here in this case, containing one electron in this orbital. So this is the scenario when we have one lithium atom. Then, if we have that two lithium atoms combined together, according to the molecular orbital theory, so we have two atomic orbitals for each lithium atom, and then they can combine, generating a bonding combination and also an anti-bonding combination. So the atomic orbitals represented here by the arrows in each lithium atom, they combine to generate molecular orbitals shown here. And then these molecular orbitals extend and they are distributed over the entire lithium-2 molecule here, the hypothetical combination of two lithium atoms. And then as we have one electron in each atomic orbital that makes up this bond, these two electrons then occupy the molecular orbital formed by the bonding combination, which has, and therefore the overall energy of the system is lowered relative to the individual atoms. In a similar way, if we combine 3 lithium atoms, we end up with 3 molecular orbitals. So the number of molecular orbitals is the same as the number of the atomic orbitals that are combining to generate these molecular orbitals. So if we have 3 atomic orbitals combining, we will have 3 molecular orbitals as a result. So here, if we have one more lithium atom to give this lithium-3 molecule, we will have the formation of 3 molecular orbitals, having this distribution of the electrons. If we have 4 lithium atoms, we will then have 4 molecular orbitals with this kind of distribution of the electrons here. Because this orbital is half filled, we will see that when we start to combine the different atoms together, the electrons go into the bonding combination, which enables the overall energy of the system to be decreased relative to the individual orbitals. So if we continue this process, adding 5, 6, 7, 8, 9, 10, 100, 1,000, 1,000,000, and so on, we arrive in a scenario that we have n lithium atoms, which is a very large number. And in this case, this comprises the scenario in which we have a solid material. So you can see here also that when we increase the number of lithium atoms combining to generate these molecular orbitals, the spacing between these molecular orbitals also decreases. Therefore, when we get in the scenario of a solid material in which we have a combination of a very large, very large number of atoms, we end up in a scenario that instead of having these discrete energy levels forming by the combination of the atomic orbitals to generate these molecular orbitals, so instead of having these discrete energy levels, you have, because we are combining any number of atoms, which is a very large number of atoms, you have a very large, very large number of these orbitals that are generated as a result of the combination of the individual atomic orbitals. And because of this very large number of orbitals, they will be very closely spaced together. So the spacing between them will be very, very, very low. Therefore, the result is that because these energy differences are very low and then they are very close in energy to each other, the electrons can freely move between these energy levels. Therefore, instead of having these discrete energy levels, what we have is that we have a continuous range of energy levels in which the electrons can move freely move. So in this case, we have a continuous range of energies that comprise these orbitals. In other words, we have an energy band, how it's called by the band theory. So we have an energy band here formed by the bonding combination of the n atomic orbitals or from an infinite number of individual atoms, and a band formed by the anti-bonding combination of this very, very, very large number of atomic orbitals to form the solid. So in the solid, instead of having these discrete energy levels, we have a continuous band of energy or a continuous band of energy where the electrons are located. So basically, this is the concept or the fundamentals of the band theory to describe the bonding in solids. So this is the scenario for a metal. So we have the band here half filled in this case. And then this is what gives like the very interesting properties for metals. So many properties that we observe from metallic materials, they come from this, from the bonding or the formation of these bands of energies, and in particular, as a result, therefore, of the delocalization of the electrons through the solid, because in these bands of energies, the energy levels are very close to each other, so the electron can be freely moved along the solid material, and therefore we have delocalization of electrons over the entire structure. This gives rise to the fact that metals are malleable or easily deformed by an application of pressure, and ductile, which is the property to be able to be drawn into a wire. Also, electrons can rapidly adjust to the relocation of the metal nuclei, and there is no directionality, specific directionality in the bonding. And another interesting property is that metals, therefore, they are lustrous because the electrons can respond almost freely to an incident wave of electromagnetic radiation and then can reflect it. So basically, the electrons are freely to move along the structure, and in this case, we can approach the electrons as being freely able to move with respect to a fixed lattice of positive species, which are the metal nuclei, for example. So this is for metals, right? But in the case of ionic compounds, or in the ionic compounds, we have then ionic bonding, in which the different elements, they are held together by rigid symmetrical arrays that in which the bonding there, or the interaction between the different components, is electrostatic. So the interaction comes as a result of attraction between opposite charges, because the in ionic bonding, we will have a cation and an anion, so positive and negative charges. So the different elements are held together in this rigid ordered arrangement in the solid as a result of these interactions or electrostatic interaction between spheres or atoms having different charges. And it's important to mention that, of course, ionic bonding depends on the presence of ions. So it depends on process of electron loss and electron gains. And therefore, this is found mostly in solids made of combinations of metals with more electronegative elements, so that we can have metallic or ionic bonding to take place. One important aspect here that will be important when we discuss ionic and metallic bonding structures is that both the ionic and metallic bonding in the solids, they are non-directional. Therefore, in this case, we can describe the structures of both metallic and ionic solids in terms of space-filling modules that maximize the number and strength of the interactions between atoms or ions. So we can understand these structures based on models in which atoms considered that can, in which each atom is regarded as a hard sphere or a sphere. And then we can construct this structure based on space-filling modules in which these spheres organize together into 3 dimensions to occupy the space in a more effective manner, maximizing the number of spheres occupying a designated space and maximizing the strength of interactions between them. Okay, so this organization of these hard spheres in space usually occur in a regular manner, so generating a regular array of atoms, ions, or molecules in the solid, and therefore this regular array of atoms, ions, or molecules in the solids that is usually observed and produce these structures, such as ionic and metallic solids, they are usually represented by a repeating unit. So in now all the structures that are based on a regular distribution of atoms, ions, or molecules along the 3 dimensions, these regular arrays are usually best represented based on a repeating unit, or the smallest repeating unit that can be used to describe the structure of the material along the 3 dimensions, only based on translation movement or translation operations. And then this repeating unit is called the unit cell. So the unit cell represents the smallest unit or the smallest part of the structure or the smallest portion of a structure of a solid that can be employed to describe the overall structure of the material. And then we will see this more clearly in examples in the upcoming slides. So we talked about the metallic solids or metals that are held together by metallic bonding, and then we saw the band theory to explain this metallic bonding. We saw that inorganic solids then are held together by electrostatic interactions that comes from the interaction between opposite charges in cations and anions that make up that make up this solid. And in the case of the covalent, another class of solid materials is the covalent network solids. And then in this case, these covalent network solids, they are held together in this case by an extended network or of covalent bonds. And this type of bond result in materials that are hard, like diamond. Another type of solid material is the molecular solids that are held together by intermolecular forces. So the molecules interact. So each molecule is the repeating unit or the building block to make the solid, and the molecules themselves interact together by intermolecular forces, which are dispersion forces, dipole-dipole interactions, and hydrogen bonds. And because these interactions are relatively weak, these molecular solids tend to be soft and have low melting point. So this is a diagrammatic representation of these different kind of solids that we just discussed. The metallic solids, in which metals are held together, forming metallic bonding, in which the electrons are delocalized over the structure. Ionic solids containing cations and anions held together by ionic bonding. Covalent network solids, in which they are held together by covalent bond. And molecular solids, in which molecules represent the building blocks to make the solid, and they interact together by intermolecular forces. So there is a question here in the chat. I will read to everybody. Can you clarify the explanation why metals can transfer electricity in terms of free electrons? Yes, so they are good electrical conductors because the electrons can move freely along the structure through these bands of energies. So if we apply potential and apply current to a metal, we can have that the flow electrons can occur can occur easily, given this property of being a good conductor, due to the free movements of the electrons through the energy, to the bands of energy. All right. So now let's start to talk in more detail about the structure of the solids. So let's study now the structural arrangements that are common for solid materials, and then we will focus on metals first, and then we will switch or go towards inorganic solids. So the structure of solids is determined by the arrangement of atoms in the solid. So if we are talking about metals or ionic compounds, we can state that the arrangement of the atoms or ions in these solids, and then let's start with simple solid structures. So the arrangement of ions or atoms in simple solid structures can be represented by considering the different arrangements of hard spheres. So we can consider the atoms or ions as hard spheres, and then we can describe the arrangement of these ions or atoms in terms of the arrangements of hard spheres. Okay, so we can have a solid that is crystalline and a solid that is amorphous. So a crystalline solid, it means that atoms are arranged together in an orderly and repeating pattern, while an amorphous solid lack order. So we have a disordered arrangement of atoms in the structure. And most of the materials that we will be discussing are crystalline materials. And so we will focus our discussion with more emphasis on crystalline materials that represent an orderly arrangement of atoms in three dimensions. So some important definitions regarding unit cell and crystal structures, for example. So a crystal of an element or a compound. So we saw that a crystalline material has an ordered arrangement of atoms that repeats itself along space and the three dimensions. So a crystal of an element or a compound can be regarded as being constructed from regular repeating structural elements. So a crystal is made up of structural elements that are regularly repeating their pattern along the three dimensions. So we have an ordered arrangement of atoms, molecules, or ions. The crystal lattice, so the definition of crystal lattice here, which is important, represents the geometric pattern formed by the points that represent the positions of these repeating structural elements. So the structural elements in the solid can be atoms, molecules, or ions. Therefore, the crystal lattice is the geometric pattern formed by the points, and each point represents the position of the atoms, molecules, or ions in the solid, which comprise the repeating structural elements. So the lattice represents a three-dimensional infinite array of points, which are the lattice points. And each one of these lattice points is surrounded in an identical way by neighboring points because the structure is ordered and repeating along the three dimensions. So the lattice defines the repeating nature of the crystal that we have for the structure that we are dealing with. So if we are talking about the crystal structure, so the crystal structure itself, it's obtaining by associating one or more identical structural units, such as atoms, ions, or molecules, with each lattice point. So the unit cell here of a three-dimensional crystal or ordered solid material, it's an imaginary parallel-sided region, or the smallest region in the material or in the crystal, in which the entire crystal can be built up by purely translational displacements. So the smallest unit or the smallest portion of the solid material that can be used to describe the entire structure of the solid by purely moving into the space with three dimensions. So it's the relatively small repeating unit. So the unit cell, it is the relatively small repeating unit from which the structure of the crystal can be built by stacking this unit over and over in all three dimensions. And therefore, the structure of a crystalline solid is defined by the size and the shape of the unit cell and by the location of the atoms within the unit cell. So these are two important parameters to define the structure of a crystalline solid, the size and shape of the unit cell, and the locations of the atoms within the unit cell. So, like if we have a ordered solid material, which has like an ordered arrangement of atoms. So here in this figure, we have an ordered arrangement of anions and cations, represented here by spheres of different colors. So if we try to define the unit cell here, or the smallest unit from which the entire solid material can be described, we can see that the unit cell may be chosen in a variety of ways. So in these two cases, these two regions can be defined as the possible unit cell, but generally it's preferable to choose the smallest cell that exhibit the greatest symmetry. So in this case, the smallest cell would be this one. So this would be the preferred choice for the unit cell in the material. And in 3 dimensions, the lattice is defined by 3 vectors, A, B, and C, and they describe the different dimensions of a unit cell. So they define a unit cell that is a parallelepiped, that is a parallelepiped, or that is parallelepiped. So the unit cell, therefore, is described by the lattice vectors or lengths A, B, and C on the cell edges, right? And also by the angles between the edges here of these lattice vectors. So the angles that these axes form with each other. So here, the lattices are defined by the 3 lattice vectors, or these lengths of the unit cells in 3 dimensions, and also by the angles in which between these edges, or between the lattice vectors. So here, for a cubic lattice, for example, the 3 lattice vectors A, B, and C have the same dimension, so they are can be represented by A, and A. And the angles alpha, beta, and gamma, they are equal to each other, and they correspond to 90 degrees. In the tetragonal lattice, A equals B, which is different than C. And all the angles are equal, corresponding to 90 degrees C. Therefore, like by using these descriptions, we can find that all solid materials can be represented by 7 crystal systems, as described here in this figure. So we have 7 crystal systems based on the edge lengths or lattice or the lattice vectors, and angles between these edges. So based on this description, we can find that we have 7 crystal systems that can be used to describe all ordered structures or all solid materials having a crystalline structure, in which these angles, alpha, beta, gamma, and the lengths A, B, and C are used to define, or they are employed to define, the size and the shape of the unit cell relative to the structure of the solid. And these And these lengths, A, B, and C, and these angles, alpha, beta, and gamma, relative to the origin of the axis, for example, can be employed as descriptors or are called the unit cell parameters, or the parameters that define the unit cell. So the unit cell is defined by the lengths A, B, and C, and the angles alpha, beta, and gamma. So here we have how the relationship between the lattice parameters, both the edge lengths and the angles for the seven systems, the seven crystal systems that we just described. So we go from the most symmetrical, which is the cube, to the least symmetrical, which is the triclinic. Here we have a comparison of all these unit cells. And okay, so let's take a look also at some so here we described the sizes and the shapes of the unit cells. Now we can describe, we can take a look on how many atoms can be present in each of these unit cells, or the atomic arrangement, or the arrangement of atoms, ions, or molecules in each of these unit cells, because we saw that the structure can be defined by the size and shape of the unit cell, and then how many atoms are present, or the atomic arrangement inside the unit cell. So let's take a look now on how these unit cells, or how the atoms, ions, or molecules, which are the building blocks of the unit cell, or the lattice points here for each one of these unit cells, can be arranged in a unit cell. So a primitive unit cell, which is denoted by the symbol P, has just one lattice point in the unit cell, which means that we have only one atom, ion, or molecule in the unit cell. Because in this case, for the primitive unit cell, the lattice points, which can be atoms, ions, or molecules, which are the building blocks of this unit cell, they are located only at the corners of the unit cell. And then, of course, this is a unit cell. So in the unit cell, this is the smallest repeating unit that can be described to describe the structure of the solid. So each atom here, or each lattice point here at the corner of the unit cell, is actually shared with 8 other unit cells. So the result is that these 8 atoms at the 8 corners here, actually, this indicates that we have only one atom per unit cell. So the primitive unit cell, the atoms, ions, or molecules, or the building blocks are located only at the corners of the unit cell. We also have centered lattices, which are generated by placing an additional lattice point or additional lattice points in specific locations of the unit cell. So in addition to the atoms or the lattice points only at the corner, for the centered lattices, we also have additional lattice points in specific locations. For a body-centered cubic lattice, we have one lattice point right in the middle of the unit cell. So we have the lattice points at the 8 corners and a lattice point right at the middle of the unit cell. So we have 2 atoms here per unit cell. Another type of lattice is the face-centered cubic lattice, in which, in addition to the lattice points at the corners of the unit cell, we also have a lattice point at the center of each one of the faces. Okay, so we have lattice point at the corners and at the center of each face of the unit cell. So here we have a representation of these different structures. So here, for example, we have a metal atom as the building block. So this metal atom then arranges into three dimensions, into a ordered structure that can be a primitive lattice, a body-centered cubic lattice, in which we have, in addition to the atoms on the corners of the lattice, an atom in the center of the unit cell, and or a face-centered cubic lattice, in which, in addition to the atoms on the corners of the unit cell, we also have one atom in the middle or in the center of which one of these faces. And then this gives rise to different kinds of crystal structures. So the primitive cubic metal, the body-centered cubic metal, and the face-centered cubic metal structures for this case. Also, I would like to show you an interesting website that you can use to visualize these things in 3 dimensions. So is everybody seeing my browser now, right? I hope so. If you guys are still seeing the PowerPoint, let me know. So there is this website that I posted the link on the Moodle page already, called chemtube3d.com. So you can come here to Inorganic, and then you can see here, we can see they have examples of different kinds of structures that can be visualized here in 3D on the computer screen. So if we choose, for example, the simple cubic structure, which is the primitive unit cell that we just saw, it's here. So we can visualize, move around, and see it very well. So we see here the unit cell having, and then the atoms or the lattice points only at the corners of this unit cell. We can also see here a body-centered unit cell, in which, in addition to the atoms at the corners, we also have one atom or one lattice point in the middle of the unit cell. And also we have the face-centered cubic lattice, in which, in addition to the atoms at the corners of the unit cell, we also have one atom in the center of each one of the faces of the cube. Okay, so I highly recommend that you guys check this out, because this is very useful for visualization in 3 dimensions. So everybody is back to my PowerPoint now, right? I hope. All right, so let's take a break now. It's 1:05. So let's take a 10 minutes break and be back at 1:15, okay? So I will see you guys at 1:15. Hello, everyone. So welcome to the second part of our lecture today. So we have just discussed the different types of arrangement of the atoms in the unit cells, which gives us 3 different types of crystal lattices: the primitive cubic lattice, in which all the lattice points are concentrated at the corners of the unit cell; the body-centered lattice, in which, in addition to the lattice points being present at the corners, we have a lattice point in the middle of the unit cell, and the face-centered lattice, in which, in addition to the lattice points at the corners, we have a lattice point also in the center of which one of the faces in the unit cell. So an important parameter, therefore, that comes from this discussion is that this enables us to understand the number of lattice points that are present in a unit cell. So, for example, a lattice point that it's in the body of a unit cell. So in the body of a unit cell, it means that the lattice point is fully inside the unit cell, as we saw for the body-centered crystal lattice. Then we have that in this case, the lattice point in the body of the cell belongs entirely to that cell, so it counts as one in terms of the number of lattice points per unit cell. A lattice point that is on a face of a unit cell is shared by two cells, so contributes to half to the unit cell that we are describing. A lattice point on an edge is shared by 4 cells, hence it contributes with 1/4. And the lattice point at the corner of a unit cell is shared by 8 cells. Therefore, it contributes to 1/8 to the unit cell. So here we have a representation of the location of the atoms, corner, edge, face, or anywhere else, number of unit cells sharing that atom, and the fraction of the atom within the unit cell that we are talking about. So corners shared by 8 unit cells, face by 2, edge 4, and anywhere else 1. So a primitive cubic unit cell has 1 atom per unit cell. A body-centered cubic cell has 2 atoms per unit cell, and the face-centered cubic metal has 4 atoms per unit cell. All right, another important concept here when dealing with the structures of solids is the fractional coordinates and the projections. So we can define the position of an atom in a unit cell in terms of fractional coordinates, which are expressed in terms of a fraction of the length of a side in the unit cell. So the fractional coordinates for an atom can be expressed as a fraction of the length of a side of the unit cell. Therefore, the position of an atom relative to the origin, so if we set the origin here in this point, and then we say that this is the A axis, B axis, and C axis, for example. So the position of an atom relative to the origin will be located at XA, parallel to A, YB, parallel to B, and ZC, parallel to C. And these will be denoted as X, Y, and Z, with X, Y, and Z between 0 and 1, because here on the unit cell, we have unity. So the entire length of A, B, and C in the unit cell corresponds to 1, or unity. So this atom, for example, here in the center of this body-centered cell, it is located at +½ in terms of A, +½ in terms of B, and ½ in terms of C. So the fractional coordinate is +½ ½ and ½. And another thing is that is usually employed in terms of projections in this case is that sometimes a more clear method to represent three-dimensional structures on a two-dimensional surface is to draw the structure in projection by viewing the unit cell down one direction, typically one of the axes in the unit cell. In this case, if we use this projection, the position of the atoms relative to the projection plane are denoted by the fractional coordinate above the base plane and written next to the symbol defining the atom in projection. So we'll see an example of that to make it more clear. So if two atoms lie above each other, then both fractional coordinates are noted in parentheses. So one example is this body-centered structure. So here we have, for example, we are seeing the structure from the top. So let's say from this kind of axis. So what happens is that we have here an atom below and above. So on fractional coordinate 0, and here on fractional coordinate 1 in this position. Here the same, and here the same. And then here we have an atom in fractional coordinate half relative to this axis that we are using, relative to the origin in the axis that we are using to visualize the structure. So this kind of structure can be represented in two dimensions by this type of projection, showing here the fractional coordinate along the axis that we are using from the axis that we are using to visualize and describe the structure. So, for example, if we have this kind of structure, we have, like, if we draw this in projection, then we can have here, and then seeing, for example, from this direction, for example, we have atoms here at the corner with fractional coordinate 0 and 1, atoms here along this region with fractional coordinate half, and also on the other side as well with fractional coordinate half. And in the middle, also atoms with fractional coordinates 0 and 1. So there is an atom in fractional coordinate 0 and an atom with fractional coordinate 1 relative to this axis that we are using to visualize the structure. And once again, to see those things is very useful to use these models or projections or physical models as well to better visualize those things, because on paper sometimes it can be a little challenging. All right, so let's now discuss the close packing of these hard spheres that are used to represent atoms or ions in metallic and ionic solids. So in metals and ionic solids, many of them, they can be regarded as being constructed from atoms and ions that are represented, or that can be represented by hard spheres. In this case, we can use this because in this kind of solids, we don't have directional covalent bonding, in which the spheres that represents the atoms or ions, they are free to pack together as closely as possible and as closely as the specific geometry allows it. So in this case, that's why it's called a closed packed structure. It's because it's when we are arranging these atoms or ions represented by hard spheres, they pack together as closely as possible, generating a closed pack structure, which means a structure in which we have the least unfilled space, or that makes the packing as efficient as possible. So let's consider first a single layer of identical spheres. So let's see how we can pack these hard spheres on space to generate this closed packing. So let's consider like a first layer of hard spheres, and then this is the closed packed layer that we can generate for this arrangement. So the greatest number of the most efficient way in which we can arrange a single layer of spheres, of identical spheres, is this arrangement, in which we have 6 immediate neighbors for each sphere. So this is the only way to construct this closed packed layer, which is the most efficient way to pack a single layer of identical spheres. Okay, so we have here, therefore, another representation of this closed packed arrangement of spheres in one layer, in which we have 6 immediate neighbors for each one of the sphere. Okay, so if we come, so note that like each one of these sphere in the layer is identical with 6 other placed around it in a hexagonal pattern. And then remember that this also repeats itself along the the all dimensions. So if we consider, if we use this single layer of spheres packed in a closed packed arrangement like this, let's use this as the building block to construct our solid. So if we come with a second closed packed layer of spheres, we can, the most efficient way to pack this is to put this second closed packed layer above the first layer, but in the dips between the spheres of the first layer, so that each sphere in the second layer touches 3 layers in the layer below. So the most efficient way would be to put the second layer in the dips between here, in the dips formed within the first layer, so that each sphere in the second layer touches 3 spheres in the layer below. But note that when we do this, we can see that only half of the dips in the original layer are occupied, as there is insufficient space to place spheres into all dips. So some of the dips here remain not occupied. So only half of the dips are occupied. So in this case, the arrangement of the spheres in the second layer is identical to that in the first, each sphere with 6 nearest neighbors. And here, the only difference is that the pattern is slightly displaced horizontally, so that the second layer sits on half of the dips formed in the first layer. Okay, so now if we add a third closed packed layer, we can put this third layer in 2 different ways, remembering here that only half of the dips are occupied, right? So we can put these third layers in two ways, and this gives rise to either one of the 2 polytypes or 2 structures that are the same in 2 dimensions, or in these 2 layers, but different in the third. So in the first case, we can add the spheres of a third layer of a closed packed arrangement of spheres. We can put this in the first scenario, we can put this third layer above the dips that were not occupied in the first layer, like this. So we occupy half of the dips with the second layer, and then with the third layer, we occupy the remaining dips. So the second layer fits into half of the dips of the first layer, and the third layer lies above the remaining dips. So in this case, we have an arrangement ABC, 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 which repeats itself along the solid. So C denotes a layer that has spheres that are not directly above the spheres of the A or the B layer position. So they are all displaced with respect to one another. And this pattern, therefore, corresponds to a structure having a cubic unit cell, and therefore this is called cubic closed packing. Because each cubic closed packed unit cell has a sphere at one corner and one at the center of each face, this is represented by the face-centered cubic unit cell. So in this kind of structure, so this is a cubic closed packing, face-centered cubic arrangement. So in this case, this is another representation of this structure of the layer A, layer B, and layer C. So in this case, the coordination number for each one of the atoms or spheres comprising the solid here is 12. So we can have 6 atoms from the touching spheres in the original closed packed layer, plus 3 from above and 3 from below. So here we have 6 here in the original layer, plus 3 from above and 3 from below, giving coordination number 12. Okay, and this can also be well visualized by this in this website that I showed you, in which we can click here to ABC layers, in which we can see this stacking of layers in a more clearer way, in which the different layers ABC are shown in yellow, orange, and red here. And yeah, all right. So in these kind of structures, the idea is to pack these spheres as efficiently as possible on space. That's why it's called closed packing. And in this kind of structure, having this face-centered unit cell, the occupied space in a closed packed structure, in this case, accounts to 74% of the total volume. So 74% of the total volume is occupied by atoms, by the sphere. And so this is calculated by dividing the total volume of the atoms occupied in the unit cell by the overall volume of the unit cell. But in a real solid, this remaining unoccupied space is not empty. And the type and distribution of these spaces between the spheres are known or are called as holes. They are also very important because in many structures, including alloys and ionic compounds, they can be regarded as being formed by expanded closed packed arrangement in which additional atoms or ions can occupy all or some of these holes or empty spaces in these closed packed structures. So here we have like another illustration of this arrangement in space, the cubic closed packing. So here, the different ABC arrangements. And then here we have the visualization of this ABC pattern of layers with respect to the unit cell of a face-centered cubic structure. All right, so I mentioned that there is this 74% in packing efficiency for this kind of a unit cell. And then actually we can calculate the occupied space in a closed packed array. So this can be done. So here we have the representation of the face-centered cubic unit cell, in which the edge lengths of the unit cell here can be represented by A, and here the diagonal can be represented by B, and here in the diagonal, we have that the atoms touch themselves along the diagonal of a face. So B here, the diagonal corresponds to 4R, in which R is the radius of the atoms. So the packing efficiency here for this closed packed array is therefore the volume of the atoms, or the volume that the atoms occupy in the unit cell, divided by the volume of the unit cell. So the volume of all the atoms in the unit cell. So in this case, face-centered cube, we have 4 atoms. So the 4 times the volume of each atom, 4 thirds of PR to the cube, divided by the volume of the unit cell, which is A to the cube, right? Because it's a face-centered cubic unit cell. So here we have B, here's the diagonal of the face. It relates to the edge length through this expression. So we have that this corresponds to B, and B is equal to 4R. So we have that A is equal to this value for this unit cell. So when we replace this into this equation again, we have this, and then if we do this calculation, we should arrive at 74% of packing efficiency. So in another scenario, so we have one layer of closed packed structure, and then we have the second layer that is within the dips of that it is within half of the dips of the first layer. And this, in this other scenario, then we can add this third layer directly above the spheres of the first layer, and therefore each sphere in the second layer gains 3 more neighbors in this layer above it. So in this case, the third layer is placed directly above the first layer. This gives, therefore, a pattern of AB, 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 because the third layer is positioned directly above the first layer, right? So this kind of an arrangement gives hexagonal unit cell, actually, and in this case we have hexagonally closed packed structure, or hexagonal closed packing. And this is another representation of this hexagonal closed packing, and then we can see here the repeating nature of the third layer. So we have a AB, AB, AB kind of arrangement. And this is another representation of this hexagonal closed packing, which is also very important for the description of structures of solid materials. And then we also can visualize this here better in 3 dimensions through this website that I suggested to you guys. And then we can see here also the arrangement of the layers very well. Okay, all right. So in summary, we can see that therefore this we can arrive in these two types of very important structures: cubic closed packing and hexagonal closed packing, considering this stacking of layers containing a closed packed arrangement of spheres. So we start with one of those closed packed layers in which each sphere is in contact with six others. The second layer then sits in the dips of the first layer, in which half of the dips are occupied. And for a cubic closed packing, the third layer is placed above the remaining dips that remain unoccupied, given an ABC type of an arrangement. And in the hexagonal closed packing case, this third layer is positioned directly above the atoms of the first layer, giving an AB type of arrangement. And if we take a look also at this single layer of closed packed sphere, we can see that there are two types of depressions here, or dips, between the spheres. So this is where the B layer comes, and this is where the C layer comes. All right, and another important subject regarding the description of these structures is also the depositions or the distribution of the holes in these closed packed structures. So the feature of a closed packed structure that enables us to extend the concept of using this closed packed arrangement of hard spheres to describe more complicated structures is that the existence of their holes, or two types of holes, or unoccupied space between the sphere. So in these closed packed structures, there can be two types of empty space, or two types of holes between the spheres. We have octahedral holes and tetrahedral holes. So an octahedral hole lies between two triangles of spheres on adjoining layers, as described here, octahedral. So we have coordination number of 6 for this hole. So for a crystal containing an n number of spheres in a closed packed structure, we will have an n number of octahedral holes. So this is a better way to visualize this hole, or by changing the arrangement a little bit. So these are different ways to visualize this octahedral hole. So if we go back here to the our cubic structure, we can visualize the hole here, the octahedral hole, easily. And then we can make here the space filling model. Now this is more complicated. So the octahedral hole is right at the middle there. So we have 1, 2, 3, two atoms here in this direction and 4 atoms here, giving a total of 6. Coordination number of 6 for the holes. We can try to see another view here with an adjacent unit cell. And we also have the tetrahedral holes that it's formed by a planar triangle of touching spheres capped by a single sphere lying on the dip between them, as represented here. So these tetrahedral holes can be divided into 2 sets, one with the apex of the tetrahedron is directed up, and the other the apex points down. So if we have an arrangement of n closed packed spheres, there are n tetrahedral holes of each set, and 2 N tetrahedral holes in all. So this is a representation of these tetrahedral holes in the structure, and those can be also visualized by looking at this figure. And then I also recommend you guys to check these models, or even like physical models for this arrangement, so that you can play around and visualize these positions very clearly. So here we have, for example, in the structure where the tetrahedral hole is. Okay, and then this is another way to represent here the octahedral and the tetrahedral sites in the structure. So here we have 3 spheres and 1 sphere below on the dip between these 3 spheres. So this is a tetrahedral hole, and this is an octahedral hole. All right, this is another way to, I'm trying to put several different ways to represent these holes, because I know that explaining here, like on the PowerPoint slide, is very difficult to understand and visualize these things. That's why I'm recommending the websites and the models. And here is a demonstration of another demonstration of the position of this tetrahedral and the octahedral holes in a closed packed structure. Demonstrating for N spheres, we have N octahedral holes and 2 N tetrahedral holes. All right. So in this, so far, we have discussed only the scenario in which we have the hard spheres, and then all the spheres were identical. But we also have the scenario in which we have 2 different types of hard spheres having different ratios that they are packing together. And this is important in the context of ionic compounds, for example, or ionic solids, in which we have the stacking of cations and anions, right? So in this case, when we are talking about spheres of different sizes, like when we have the stacking of cations and anions, actually, what happens is that the larger spheres, which are the anions, usually formed a closed packed array, as we just discussed, and then the smaller spheres, the cations, occupy the octahedral and tetrahedral holes. This is why this model, these simple models of stacking of hard spheres is so useful and so important, because it applies not only to metals, but also to ionic solids as well, in which we approach, or we can describe the structures of these materials, but by still a closed packed arrangement of spheres, in which the larger spheres that are the anions form this closed packed array, and then the cations occupy the holes, octahedral and tetrahedral holes. Therefore, for simple ionic structures, we can describe these structures based on closed packed structures, or based on the occupation of holes in these closed packed structures. And then, even though we focus on these closed packed structures, it's important to mention also that not all metals have structures that are based on closed packing. And some other packing patterns that in which the space is not used as efficiently as in the closed packed can also be observed. And even for metals that have closed packed structures, we can have a phase transition to a less closely packed structure when they are heated, or when the atoms suffer large amplitude vibrations. One common adopted arrangement has the translational symmetry of a body-centered cubic, lattice and is known as the body-centered cubic structure, in which a sphere is at the center of your cube with other spheres at each corner. So this is the body-centered cube structure, and then we can see that in this case, we don't have closed packed arrangement. We have coordination number 8, which is less closely packed than the cubic closed packing and the hexagonal closed packing structures that we just described, in which we have coordination number of 12. And then in this case, we have 32% of the space unfilled, compared with only 26 in the case of the closed packed structures. And this is adopted, this kind of structure, by 15 of the elements, including all the alkali metals and metals of group 5 and 6. And this type of structure is also referred to as the tungsten type structure. Also, a least common metallic structure is the primitive cubic structure, in which the spheres are located in the lattice points of a primitive cubic lattice, taking the corners of a cube. The coordination number in this case is 6, and the packing efficiency is pretty low. So this is rare, only observed for polonium, for example. And then in this kind of structure, we have 48.7% of empty space. So this will be the arrangement of a cubic, a primitive cubic structure. So here we have a comparison for closed packed versus non-closed packed structures, with the changes in the packing efficiency being very clear and very visual already by just looking at the slide. And then we can also observe this by changing by the variations in the coordination number for these types of structures. So many of the metals formed closed packed structures, indicating that the bonds between the atoms have little directional covalent character. And here we have illustration here on the periodic table for the different structures that are adopted by several of the metals. For example, seeing here that the primitive cubic is only achieved for polonium, and then the most of the materials have either the cubic closed packed or the hexagonal closed packed structure, except the alkali metals. All right, so I think we should stop right here before we continue. So from next class, we will continue our discussion, and then we will start by describing the polytopism. So I think for today, I will stop here. I would like also to remind you guys that I already posted on Moodle homework 3, dealing with oxidation and reduction. So I posted it today. So that homework is due in 2 weeks from today. All right. And then you guys also have a homework 2 already ongoing. So please don't leave to make the homeworks to the last minute. All right. So this is all that I had for you today. So does anybody have any questions before we wrap up? Well, if not, thank you very much, everybody. And then I will see you guys on Friday, okay? All right, thank you very much, everyone. See you.